Hello, everybody. Welcome back to Calculus 1 online at Frederick Community College with Professor Lockman. We just finished a big task of learning and mastering various rules for computing derivatives. And let me remind you that we finished that module with a discussion of logarithmic differentiation. Now, the next natural step in a study of calculus would be to consider various applications of derivatives, and that's exactly what we're going to do in this lecture and few other lectures that follow it. So today we will talk about related rates. So first, I would like to discuss an example in order to motivate this idea of related rates. Suppose we have a spherical balloon that has been filled with air at a constant rate, and here you have a visual representation of this scenario where we have three different times, and at each time, going from time 1 to time 2, the balloon is increasing in size. Now we also have two quantities that characterize this balloon. We have the radius that's marked by R1 at time 1, R2 at time 2, and R3 at time 3. And we also have the volume, so the amount of space taken by the balloon that's also marked on the picture by V1, V2, and V3. Okay, so what is the idea here? If we know the rate of change of one of these quantities, for example, let's say we know how fast the volume is increasing. And we also know the relationship between R and V, hence the word related, then we should also be able to find the rate of change of R. Okay, so that is the big idea here. Whenever you have a relation between two quantities and you know how one of them changes, whether it's increasing or decreasing. In this scenario, we clearly see that the volume is increasing. Then we should be able to find the rate of change of the other quantity. Okay, so that's the basic idea. Let's go ahead and talk about problem solving strategy that we are going to follow. So first we're going to write out all the constants and variables. So constants are numbers. Variables is something that we're going to assign. For example, R for radius, V for volume. We assign letters to the variable quantities, and if needed, we draw a picture. Then we state the relationship between the variables. So this will be typically a formula from either geometry or physics, something that we are well aware of, or if there's no assumption that you might know this formula, the formula will be given to you. Okay, so we will write down the relationship between the two variables and what we know about the rates of change. Now, let me remind you that rate of change, all it is, it's the derivative, okay? Then we find the equation that relates the variables together. And at the next step, we implicitly differentiate the equation with respect to the independent variable. And let me go ahead and emphasize it here that in our problems, the independent variable will be time. Okay, so t for time. And then we find the values of the variables at the desired point, substitute into the formula, and compute the unknown rate of change. Okay, so this is a nice problem solving strategy that we should follow. And once again, at the moment, it might not make too much sense to you. It will make a lot more sense once we take a look at the problems. So that's what we're going to do for the rest of this lecture. There are 4 different problems that we're going to discuss. Let's go ahead and get started. Okay, let's take a look at our first example that is directly related to the problem we just discussed on the previous slide. A spherical balloon is being filled with air at the constant rate of 2 cubic centimeters per second. how fast is the radius increasing when the radius is 3 centimeters. So let me remind you what a visual representation of this scenario would look like. We have a balloon that's been filled, and at different times it gets bigger and bigger as time increases. All right, so how do we approach this problem? Let's take a look at the solution. The first thing that I'm going to do is introduce some variables. So very natural to say that V is the volume of the balloon. And then from geometry, I recall that we have a formula. V is equal to 4/3 times pi times r cubed. Okay, now what else do we have? We have the rate of change of V, and that's given right here, constant rate of change, and it is 2 cubic centimeters per second. So really this quantity right here, it is just V prime of t. Let me remind you that we do have this independent variable here, t, which stands for time. Now, what other variable do we have? R, which stands for radius. So the two quantities that we need to relate are radius and volume. And each one of those is a function of time. So my relationship is this equation right here, V of t equals to 4/3 times pi times r of t cubed. Okay, so that is the relationship that we're going to use in order to find the rate of change of the radius. Now, the next step is to differentiate each side of the equation, keeping in mind that each of these functions is a function of time. So on the left, we get V prime of t, which we do know. We know this quantity. It's right here. On the right side of the equation, we apply the power rule and also chain rule. So we have 4/3 pi times 3, that's me applying the power rule, times r of t squared, and times the derivative of the inside, which is r prime. And let me remind you that this is exactly what we want to find, because the question is how fast is the radius increasing, so we would like to find r prime of t. So once we solve for r prime of t over here, that's just v prime over 4 pi times r of t squared. Okay, now we'll look at the problem and see which one of these quantities are given to us, and they're all constant, right? So v prime, that's 2. And I'm going to write my units here. So centimeters cubic per second. Okay, 4 pi is just a number. And then this number right here, that is the value of the radius. Okay, so 3 centimeters squared, that goes in the denominator. And notice that we get this number right here, 1/18. You can approximate if you'd like to kind of get an idea what that number is, or you can just keep it as is. Okay, but notice that also our units make sense. This is centimeters per second, right? We have centimeters cubic in the numerator, centimeters square in the denominator. So this cancels out. This becomes just centimeters per second. And this should make sense because r is just a distance, right? So it should be units per unit of time. Okay, so that's one way for us to keep track of what we're doing and making sure that our units also make sense. All right, so r prime of t in this case is 1/18 centimeter per second. All right, so here is your first example of a problem an application problem, application of derivatives, where we have two quantities. We know how one of them is changing. We have a relationship between these two quantities, and we can find the rate of change of the other quantity. Now, I want to emphasize that with these problems, the actual differentiation step is fairly simple, but the difficulties usually come in understanding what the problem is asking and coming up with the correct relationship. All right, so this is our first example. We have 3 more to discuss. Let's take a look at the next problem. We have a 10-foot ladder that's leaning against a wall. If the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? Okay, so we have the following graphical representation. We have this ladder that's 10 feet long, and we notice that we have a right triangle formed by this horizontal side right here, this vertical side, and the ladder itself. Okay, so that should give you an idea what kind of relationship we will be discussing for this problem. So let's take a look at the solution. I'm going to label each side of the triangle with a variable. So x of t, that will be the horizontal leg, okay, and y of t, that will be the vertical. And if you can imagine this ladder sliding down the wall, what's going to happen to x? That distance will be increasing, and that's why we say x prime of t is positive, okay? And then the vertical distance will be decreasing, so that means y prime of t is negative, okay? Now, what is the relationship between these unknown variables and 10? Well, we can apply the Pythagorean theorem here, and we know that in a right triangle, the sum of the squares of the two legs is equal to the square of the hypotenuse, so that is where this equation comes from. X squared plus y squared is equal to 10 squared, which is 100. Okay, so that's the relationship that we're going to use in solving this problem. Now, also keep in mind that both x and y are functions of t. Okay, so they depend on the time. So the next step is to differentiate each side of the equation. So that's this step right here. I'm applying power rule and chain rule for each of the terms. So we have 2x of t times x prime. So that's the rate of change of the horizontal leg. Okay, and similarly, we have 2y of t times y prime, and that's equal to 0 because the derivative of 100 is 0. Okay, now remember what we are interested in finding. It's saying how fast is the bottom moving along the ground, okay? How fast? So we're trying to find x prime of t. Okay, that's what we want to find out. So here at this step, 2 and 2 cancel out, and we can solve for x prime of t right here. So x prime of t is equal to negative y of t times y prime of t over x of t. Okay, so that's going to be our formula to compute x prime. Now we need to figure out what we have. Okay, so let's take a look at the actual statement. What is 2 feet per second? This number right here corresponds to y prime of t, right? So that is the rate of change of the vertical leg. Okay, now what else do we need to know? Well, we are also given that we want to find that rate of change when the bottom of the ladder is 5 feet away from the wall. So they're talking about this distance right here. Okay, so that will be x of t. Okay, so we have y prime of t, we have x of t. What about y of t? So that's the next step. I need to determine what is y when x is equal to 5, and we can do that by applying this formula, because remember, the length of the ladder doesn't change at all. It's always going to be 10. Okay, so if x is equal to 5, then y can be computed using Pythagorean theorem. So we have square root of 100 minus 5 squared, so that's square root of 75, and we can simplify it as 5 root 3. So now we have all of the values that we need in order to plug it in into that formula. So this is what we do. We have the negative here, and then 5 root 3 feet, right? So that's distance, times -2 feet per second. And why am I using -2? Let me remind you that this quantity is decreasing, which means the rate of change is negative. Okay, so that's where -2 comes from. Okay, and on the bottom we have 5 feet. So that's the horizontal distance. And let's see what happens. Okay, so what is happening here? Let's take care of the units. So feet and feet cancel out. So we get feet per second, which should make sense because we're asked to compute the rate of change of a distance, right? Distance, which distance? The horizontal one. Okay, and then 5 and 5 cancel out. So we get 2 root 3 because we have this negative and this negative, so that gives us a positive. So 2 root 3 feet per second. That's how fast the horizontal distance is changing. At which time? When x is equal to 5, right? Okay, so that's what's happening here. And notice how that rate of change agrees with this fact right here that x prime is greater than 0. Okay, so take the time to carefully go through this solution, making sure that every step is clear. And if you have any questions after reviewing this problem, definitely let me know. Let's take a look at our next example. We have two airplanes that are flying in the air at the same height. Airplane A is flying east at 250 miles per hour, and airplane B is flying north at 300 miles per hour. If they're both heading to the same airport located 30 miles east of airplane A and 40 miles north of airplane B, at what rate is the distance between the airplanes changing? Okay, so you see here a graphical representation of this scenario, and it is worth mentioning that, of course, this situation is very much simplified. So a real life problem of this type will have a little bit more complicated setup. But okay, let's take a look at the solution to this version of a problem. First, I'm going to label everything that I have in my picture. So A is the distance from A to the airport. Okay, so little a. And in our case, we know what that initial distance is, and that is 30 miles. So that's the horizontal leg of this right triangle. B, little b, is the distance from the airplane B to the airport. So B is this vertical leg, and it is equal to 40 miles. So what else do we have? We have D. In this case, that would be the hypotenuse. I chose D to represent distance between A and B. Okay. We also have speeds that are given to us. So A prime, that's the speed of the airplane A, 250 miles per hour. B prime, that's the speed of the other plane, 300 miles per hour, and we would like to determine D prime. Okay, so that's my first step to kind of label everything that I have and also assign the values. Now, what about the relationship? It is the same formula as we've used in our previous problem. So we're applying Pythagorean theorem here. So a squared plus b squared is equal to d squared. Keeping in mind that all of these quantities are also functions of t. So the next step is to differentiate each side of the equation. So what we're doing here is applying power rule and chain rule 3 times, right? Because we have the same square functions. So 2a of t times a prime of t plus 2b of t times b prime of t equals 2d of t times d prime of t. And let's remember that we are trying to find d prime of t. So on the next step, I solve for d prime of t. Now let's take a look at this formula. What is it that we have? Well, we have values for every expression in the numerator. A of t, a prime of t, b of t, and b prime of t. All of that is given to us. We just need to find the distance. Okay, how do we do that? Once again, we apply the Pythagorean theorem. Okay, we know the legs, so we can find the hypotenuse. So that's what we do in this step right here. And these numbers are picked nicely. So the answer for D is 50. And now we just plug in everything into our formula. So we plug it in over here. 30 times 250 plus 40 times 300. Divide that by 500 and we get 390 miles per hour. Okay, now let me also mention that this rate of change should be negative, right? Because the distances between the planes and the airports, and also the distance between the two planes, they're all decreasing. Okay, so this distance right here between the two planes, it is decreasing at the rate 390 miles per hour. Okay, so here's another problem where we use a right triangle and the Pythagorean theorem as the main relationship in order to find one of the rates that's related to the other rates. Let's take a look at our last example for today's lecture. Imagine the following situation. You are stationary on the ground and are watching a bird fly horizontally at a rate of 10 meters per second. The bird is located 40 meters above your head. How fast does the angle of elevation change when the horizontal distance between you and the bird is 9 meters? So here you see a graphical representation of this situation. Once again, we have a right triangle. Okay, so let's take a look at the solution. So I'm going to label all of the sides of the triangle. What do we have here? X of t is the horizontal distance or the horizontal leg of this triangle. Okay, and in this case, we say that the bird is flying horizontally at a rate of 10 meters per second. And that means for us that x prime of t is equal to 10 meters per second. Okay, y will be the vertical leg. So that is the vertical distance, okay? So the distance where the bird is above the ground, okay? And we do not know the angle. So the angle of elevation is right here. We would like to know how fast this angle is changing, okay? So that's theta prime of t. That is what we would like to find. So looking at this triangle right here, we need to determine a relationship between x, y, and theta. And there are a couple of things that we could do here. We notice that tangent of theta is opposite over adjacent. So that would be 40 over x of t. Or you could also go with cotangent of theta, which is the reciprocal of tangent, and in this case would be adjacent side over opposite. So that's x of t over 40, and that is the relationship that I'm going to choose to solve this problem. Okay, so our relationship is cotangent of theta equals to x of t over 40. So that's the next step to differentiate this equation. Keeping in mind that theta, our angle of elevation, is also a function of time. Okay, so once we differentiate left side, what do we get? The derivative of cotangent is negative cosecant times the derivative of the inside, and that is theta prime. Okay, and on the right side, this one is fairly simple. 1 over 40, we'll just pull this out, and the derivative of x is just x prime of t. Okay, so what do we have here? We need to determine how fast the angle is changing. So we're interested in theta prime of t. So once we solve for theta prime, what do we get? We get 1 over 40 times x prime of t times 1 over negative cosecant square of theta of t. Okay, now this is just the reciprocal identity for negative sine squared. So this is the equation that we're going to use to compute that rate of change. Okay, so let's inspect that expression. What do we know? We do know x prime of t that was given to us in the problem. 40 is just a number, that's fine. So we just need to find sine of theta of t. Okay, now let's see what else we're given in the problem. We are given that y is equal to 40, and we would like to find that rate of change of the angle when the bird is 9 meters horizontally away from you. So that would be x is equal to 9. Okay, so in order to compute sine of theta of t, we need to have these quantities. So if x is equal to 9 and y is equal to 40, by applying the Pythagorean theorem, we can find the hypotenuse, right? So that's where 41 comes from. Okay, now why do we need that hypotenuse? We need it because that is how we compute sine of theta. We know that sine of theta would be the opposite side divided by the hypotenuse. Okay, so what is the opposite side? It is 40. The hypotenuse is 41, so that's where this number comes from. Okay, and now we have all components that we need to evaluate that expression. So we're plugging all of that into our expression over here. So we have negative times what? X prime, that's 10, times 40 over 41 squared, and divide by 40. So once you simplify this, we're going to get negative 400 over 1681, and this is the rate of change of the angle. So that would be radians per second. Okay, and does that make sense that that angle is decreasing? Well, yes, let's think about it, but the answer is yes. Why is that so? So if you're right here standing at this point and you're not moving, but the bird keeps moving this way, then what's going to happen? So let's say the bird is right here. So now the distance is increasing between you and the bird, but the angle of elevation is decreasing, right? And let's say the bird keeps moving. Then over here, we're going to get this point. Then if we connect it with a straight line, you'll see that the distance between you and the bird is increasing, but the angle is decreasing. So the fact that it's negative actually makes sense. All right. Okay, so we'll stop right here. I hope you have a pretty good idea how to approach these problems. I do want to mention that sometimes it's a little bit tricky to figure it out where to go, what to do. So try to write out everything that you have, label all of your unknowns, put the values where they belong to, right? So identify where each number is going to go and then find the relationship. The differentiation part is usually the easy step. Okay, and also try to make sense out of your numbers. Okay, the fact that we get a negative rate over here makes sense. Okay, we'll stop right here. Thank you all for watching, and I will talk to you next time.